Now, we have seen that when a body is submerged fully or partially in a liquid, then there is a loss of weight. That is a apparent. We feel that some weight is lost. So there is a apparent loss of weight, and this principle of apparent loss of weight is called Archimedes principle. So we say that the liquid applies an upward force called buoyant force, because of which there is an apparent loss in weight. So whenever a body, solid body, whenever a body is partially or fully submerged inside a fluid, then there is an apparent loss of weight. This loss of weight is due to buoyant force. So buoyant force moves the body up, tries to move the body up, it acts upward, and so the weight, there is an apparent loss of weight. So according to Archimedes principle, the buoyant force is given by the weight of the displaced liquid. So Archimedes principle tells that whenever a body is partially or fully submerged in a liquid, there will be an apparent loss of weight, and the weight is contributed because of buoyant force, which is equal to the weight of the displaced liquid. Now, why we have a buoyant force? We have buoyant force because the pressure in the liquid increases with depth. So more we go deep, the pressure will be more and more. So thus the buoyant force is the result of the sum total of all the pressure forces acting on the body. Let us see with the diagram. So we have a liquid surface, and you see we have a body here. So I have placed this body completely submerged inside this. So here the pressure is this, and these are the pressure forces I am showing on this. So you see the pressure forces are more at the bottom and it is less. So you see the buoyant force is the sum total of all these forces, which is actually always acts upwards. So thus let us see, now we will see mathematically that how buoyant force is upward and it is equal to the weight of the displaced liquid. So now let us prove this Archimedes principle. This is the free surface of the liquid, and on this free surface, this is our submerged body. So the pressure forces are acting from all directions. Let us first see the horizontal case. So in order to see the horizontal case, I have taken a cylindrical element here. I have taken a small cylindrical element such that the cross section area of this cylinder I say dA. So you see here, this is the pressure force acting here. This is pressure P into ds1, and here we have again the pressure force P into ds2. Now let us see what is the contribution of the forces along the horizontal. Now this, you see, the total force in this direction is the force on the projection of this ds1 and ds2, which has the same area. So the total force along the horizontal is 0. So the total force, the total pressure force along the horizontal is 0. Why? Because the force that is dF1 means in this direction, that is P ds1, that projected area, that is cos theta or whatever we say, becomes, the projected area becomes dA is equal to dF2. So the total force is 0. Now we have to see what about the vertical force. So again I have taken a prismatic element, a cylindrical area here, which is, suppose this is ds, and again here again ds1, and this is ds2. So now suppose it may not be curved, suppose it is like this, the area is like this, suppose, so it may not be straight, like this it will be. So now this height is, suppose, h1, and so you see this is h2, and this height is h1, and the difference being h. So let us use this. So now we have to take this force as dF1 and again this force as dF2. So now let us calculate, let us see the force along the vertical, net pressure force along the vertical. So this is the pressure force dF2 and dF1. So let the total force here be dF is represented as dF2 minus dF1. They have in different directions. So what is dF2? What is the pressure force here? That pressure into ds1. So that pressure, that is, we can say H1 rho g into ds1, that projected area. Suppose this projected area is also dA, so that is the projected area h rho g dA, and the projected area for this surface will also come out to be, so h2 rho g dA, that comes out to be h rho g dA. This dF becomes h rho g dA. D mass, so dW, let us call it dW, which is the weight of the liquid occupied in the vertical cylindrical element. So now you see total F is that is the weight of the liquid which occupies the volume of the body, that is i.e. weight of displaced liquid. So we see that the sum total of the forces along the horizontal is 0, but when I add along the vertical, it comes out to be equal to what is the weight of the liquid in this cylinder for this element. So if I integrate it, it will come out to be the weight of the total liquid which is contained in this volume, that is displaced by the volume of this body. Thus, we have seen that the buoyant force, the sum total of all these reaction force is totally upward, and it is according to the Archimedes principle, that is the total weight of the displaced liquid. Now let us see that the buoyant force under different circumstances. So we will take up a case number 1, that a liquid under free fall. So you see, if we have a liquid in a vessel and this whole vessel is under a free fall, we have allowed it to fall freely. So what will happen? In that case, if previously a body was in this position, then it will remain in that position. If initially a body was in this position, it will remain in this position. And what will happen to the buoyant force? You see, the buoyant force was due to the pressure variation, and since there is no pressure variation in a freely falling liquid, so there is no buoyant force. So the point is, whatever the bodies were initially, if they are partially submerged, fully submerged, they will maintain their position because the liquid is under a free fall. So when a liquid is under a free fall, so in this case there is a state of free fall. So there is no variation of pressure, in the liquid with height. As a result, there is no buoyant force. Everything is in a state of weightlessness and there is no buoyant force. So there is no weight and there is no buoyant force also. So there is no relative weight this liquid will feel, so no buoyant force also. So buoyant force is the weight of the displaced liquid. The liquid itself is in the state of weightlessness, so there is no buoyant force. This is the way. Second case, a vertically accelerating fluid. So now you see, if we have a liquid and which is under an acceleration A, so what will happen to the buoyant force? Previously buoyant force was equal to weight, that is rho V is the volume of this into G. So due to acceleration, G will be replaced by G effective. So new buoyancy will be rho V G plus A. So this will be the new buoyant force that will increase. If it is accelerating downward, then G minus A. Now we will see if the liquid is accelerated horizontally. Now take up third case where the liquid is accelerated horizontally. So you see here, this is the liquid and you have given acceleration A, it is already G. So you can see the free surface of the liquid is like this, and you see this is a body which was immersed. Previously the buoyant force was B in the absence of A, but in the presence of A the free surface is this, so buoyant force B dash will be like this. So in the absence of A, B is given by B is equal to rho Vg. Now in the presence of A, B changes to B dash, that is the buoyancy is given by B dash is equal to rho V, the effective G, that is root over G square plus A square, and is normal to the free surface. So this is normal to the free surface. So the buoyancy is always equal to the weight of the displaced liquid, where weight is given by G effective. So now we will take up a fourth example where we have different layers of different liquids. Now let us take an example where a body is inside different layers of a liquid. So here we have a body. Suppose I have a body like this and it is inside a liquid. First liquid of density rho naught, and next part is this liquid. They are all immiscible liquids of density rho 2. Then this is again we have this rho 3 density, and then we have rho 4. And the part which is inside is suppose V1, the part which is inside V2, the part which is inside this V3 part, and this is V4 part. So this part is this. So we have different parts. So the net buoyant force will be given by the weight of the displaced liquid by this volume, rho 1 V1g, plus then this one, that is rho 2 V2g, plus then this, that is rho 3 V3g, plus then again this, that is rho 4 V4g. So this is will be rho I Vi g, that sigma. So thus if a body is submerged in different immiscible liquid layers, then the total buoyant force will be given by this formula. Now let us see that if something like ice is floating in water, how much portion will be inside the water and how much portion will be above the water. So if we have a solid body floating, partially floating, then how much part is inside and how much part is outside. So this is, we have a body and this is the floating body. The volume of the body is beta and eta part is inside it. This has a sigma density and the density of the liquid is rho. So consider a solid object of density rho and volume V partially submerged in a liquid of density rho. Let eta part of it is submerged. So, since the body is floating, so according to the principle of flotation, weight of the body is equal to buoyant force. So now V is the volume, so the density of the solid into volume into G is its weight, and buoyant force is the weight of the displaced liquid, that is density into volume of the displaced liquid is eta times V into G. So here Vg and Vg cancels, so we have eta fraction as sigma by rho. So eta is given by sigma for rho. Now let us take an example. For ice, sigma is equal to 0.9 and water rho is equal to 1. So the fraction which is inside is 0.9 by 1, that is 0.9. Thus 90% of the volume of ice is submerged inside the water. So when an iceberg floats, we see only 10% of the iceberg, 90% is inside the water. Now, in continuation of the fraction of a body submerged in a liquid, let us take some examples. That if we have some ice floating in water, on water, and the ice melts, what happens to the level of water? So let us take some examples where the level of water, we will see how it changes or does not changes, or how it gets affected by something melting which is floating on it. So level of water when the ice floating on it melts. So let us see that what happens to this. So you see, this is our vessel and this is water, and you see we have a block of ice of density rho of ice and rho of water. So when the ice melts, how much is the level of water changing or decreasing? Now let us see that how much is the displaced volume. So according to the principle of flotation, weight of ice is equal to buoyant force. So weight of ice, that means suppose this V is the volume of ice, that is rho ice Vg, that is equal to buoyant force, weight of the displaced liquid, V displaced G into rho of water. So volume displaced is equal to this G cancels, rho I V by rho W. So when the ice is floating, the volume of the displaced liquid, that is this much part, is given by this. Now let us see that if the ice melts. So let us see how much volume of water is created by melting the ice. So you see the mass remains constant. Suppose V volume is created. So V volume of water is created. So V into rho W is equal to, suppose this is V, we want how much V is there. So suppose this is V dash. So V dash into rho W must be equal to the mass of the ice, that is rho I Vi. That is V dash created, the volume created is equal to rho I by rho W Vi. Now you see these two quantities are the same. That means what volume is added to water is equal to the displaced volume. Thus we see, thus the level of the water will not change. So when a ice floats on water and the ice melts, then the level of the water does not change, because this cavity created will be compensated by the new water created by melting this ice. That is why the level of water does not change. Now let us see that if this ice block contains some nails on inside it and then it melts, then what happens to the level of water? Now let us see to the level of water, what happens to the level of water when we have a ice cube floating inside water and the ice cube contains some nails. We have some nails, iron nails, and so when the ice cube melts, some of these all the iron nails will sink to the bottom. So these are iron nails. So we have a ice cube with some iron nails, and when it melts, what happens to the level of water? So the point is, what happens to the level of water when the ice cube with nails floating on it melts? So when it is floating, then the weight of the displaced liquid is equal to weight of block. So you see, this is rho of water into volume of displaced liquid into G, that is the buoyant force, that should be equal to the weight of the block. Now what is the weight of the block? Suppose this is rho ice into volume of ice. So what is the volume of ice? Not the block. What is the actual volume of ice plus rho of nails into volume of nails into G. So these are the actual, and the total volume is the sum of the volume of Vi plus Vn. This. So I want, so this G cancel. Volume of displaced liquid is rho I Vi rho water plus rho nail V nail by rho water. This is equation number 1. Now when all the ice melts, the nails are floating inside it, both are deep inside water. So so they will create some mass. So next, now what will happen? Both will sink, and we will see that what is the new displaced volume. So now when the ice melts and the nail sinks, then V dash displaced will be equal to, now the nail has sinked, so how much volume of water it will displace. So now you see the VI volume of ice is going to make VI rho I VI by rho W volume of water. So this much ice will make this much water, but the nails, how much nails will displace water, we can separately calculate. The buoyant force acting on nail, so the volume of nail is this, so it will displace this much volume of nails. So the displaced water when the ice melts is this much. Now you see, let us compare V displaced initially and finally. This quantity is same, and what about this quantity? Rho of nail is more than rho of water, so this quantity is suppose 7-8 times Vn, so this is only this, so this displaced is more. So V displaced is more than V dash displaced. So previously the liquid was displaced more, now it is less. Thus the level of water decreases. The level of water decreases. Now let us take a third example where we have again the same ice cube floating in on water, but this time the ice cube has air cavities. So what will happen to the level of water if the ice with some air pockets in it melts? So again you see, it is when it is floating, we can apply principle of flotation, according to which the weight of the displaced liquid, that is rho water V displaced G, is equal to rho of ice into volume of ice into G. Air plus rho of air, volume of air into G, that is very small. So we have V displaced is equal to rho I VI by G. Now when the ice block melts, so when the ice block melts, what happens? The air pocket goes on, and then the displaced, so how much extra water is created? So extra water is created V dash, that is rho I by, this is rho water, by rho water into VI. So now you see this 1 and 2 are same, thus the level of water does not change when the ice with air pockets melts and gets added to it.